Okay, so I'm just going to give a little talk here about physics, what we were supposed to talk about today. I'm just going to mention, first of all, that the retake will have to be after the break, probably Tuesday during lunch and advisory lab that we're going to do, which I'm going to introduce at the end of this video. The Kepler's Law lab will be due on Tuesday. During class, request to do Tuesday night, and then we'll take the test on Thursday. Okay, so you can watch this video if you want to. I posted the slides on Canvas. It's good. It has to do with gravity and wicked. It's good timing. But anyway, you don't have to watch this if you don't want to. I want to start with a talk about what actually gravity does. We know that it attracts two objects. So the question becomes, what do we think actually affects the force of gravity between those two objects? So if I have object one and then I have another object, and they're big objects like planets or moons or asteroids or stars, how can they make this force bigger? Well, I think we understand that if the mass increases, then the force of attraction will grow. So if this is the original force of attraction and then this gets more massive, then the attraction is going to grow more. But how does that work out proportionally? So I have basically a link to make that, that explores that. So you can do this yourself, but we'll start with me going over it. So here we have two masses held onto by these dudes, and they're 4 kilometers away. This one's 2 billion kilograms, and this one's 2 billion kilograms, so that's quite a bit of kilograms. So what do we think is going to affect the mass? Well, we understand that if we get bigger, so if I increase this number, the force is getting bigger. If I increase this mass, it also gets bigger. You can see the number has jumped up to 80 or whatever. And then also if I bring them further apart, it gets smaller, which is probably what we predict, because if things are farther away, the attraction is weaker. If it's closer, the attraction is more, and you can see that force changing. So that's what's going on here. So let me put it back to how we started, and let's do some numerical predictions, right? So if I increase mass 1, it increases the force, but the question is by how much do I need to do it to increase the force? So does the force depend on, for example, the sum of these two masses together, or the product of them, or the ratio of them? All of those things could be features, right? So let's make a prediction. We might predict that it's going to depend on the mass of them added together, which means that in order to double the force, I would need to double the total mass. So right now the total mass is 6, but to make it twice that much, I would need to get up to 12. So I could do that by increasing this up to 6 and 6, but that actually more than doubled the force, because the force before was 33, so double that would be like in the 66, maybe 67 range. But if I get it up to, this is more than double that. However, if I double it by instead doubling this one and also doubling this one, then it does actually double the original value. So I'll play that in slow motion, or quadruple the value. So if I only double this one, it goes up to 66. If I only double this one by going all the way up to 8, it also doubles. And if I double them both, it quadruples. So it must be that it depends on the product of those two masses. And this is not obvious to people. So if I snap back here, it must depend on the product of those two values. Hello? No! Why is it not letting me write with my laser beam anymore? All right, it's scuffed. Who knows? All right. As opposed to the average of them or the sum of them or the ratio of them, it has to be the product of them multiplied together. Because independently, if I have this one, it halves the force. If I have it again, it halves the force. If I have it again, the force should half as well. So let's get back to the setting we had originally, and then let's talk about distance. So right now we're at 4 kilometers apart. If I were to have that distance to 2 kilometers, what do you think is going to happen to the force? Well, I think probably most people assume that the force is going to get bigger, but if you assumed it was going to double, you'll end up wrong. So if we imagine it's going to double if I have the distance down to 2, and then if I actually have it down to 2, the force goes up by a factor actually of 4. So it quadrupled when I halved it, which is weird. If I go the other way, if I start at 4, which is 33.4 again, and if I double it up to 8, then I get 8.3, which is not just half of 33, it's a quarter. So it seems like it's scaling by the distance between them squared. And so if I write that out, let's try this again. Is this going to work now that I'm here? Control L. No. Laser pointer. Turn on laser. Turn on pen. Oh, Shift L. I was doing Control L. I'm just a clown. Okay, so we notice the product of this, the force, is going to equal to the product of mass 1 times mass 2. And then we know it's divided by r squared. And if you think about it, it's sort of like dividing by each of their distances from each other, where that distance is measured as the distance from this center of this thing to the center of this thing. That's the distance r. We're going to call it r because later when this orbits this, it's going to look like a radius of the orbit. So that's why we use the letter r. Now the problem is if I plug in the numbers that were given in the exercise, remember this was 2 billion, so 2 times 10 to the 9th. This is 4 billion, so 4 times 10 to the 9th. Da-da-ba-da-ba-da. And then this was, each of these was 4 kilometers, so 4,000 meters, and then 4,000 meters. If I put that into a calculator, it is not going to give me close to the answer I was getting. This was giving me something like 33.4 newtons. And it's obvious that this is not going to give me 33.4 newtons. And part of the problem there is that the units don't work out. So right now on top we have kilograms times kilograms, and on bottom we have meters times meters. So altogether, this would have units of kilograms squared per meter squared. Well, newtons is supposed to be a kilograms meter per second squared. So the units on the left and right hand side of this equal sign are not right. So I need a conversion factor to convert the units for this to this. And then on top of that, it's going to do some scaling work for me. So this number that comes up is the conversion factor G. We call it the universal gravitation constant. And it turns out that no matter what you are doing with any force, if you take the mass of this object and the mass of this object divided by the distance between the two objects squared, or r times r, and then you multiply that by this conversion factor G, you will get the force of gravity on that object, assuming we're not like moving at the speed of light or something. And this G value is 67 times 10 to the negative 11th. And I'm not joking, that is actually the number. And it has units that work out to convert these units to these units. So it has to have units of like so I need to get a meter on top, a meter cubed on top. So I need meter cubed, a kilogram on the bottom, and a second squared on the bottom. So this would be the units. Meters cubed per kilogram per second squared. You're not expected to have this number memorized. It's provided on the formula sheet under constants, but that is the way that this formula works. So if I go to the next slide, it has it all sort of typed out nice and pretty. This is the number again, 6.7 or 6.67 times 10 to the negative 11th, and then it has some unit system here. Fantastic. Now, one thing that we want to talk about is this scaling with things being squared has a lot to do with things that are radiating outwards in all directions. So the strength of the gravitational pull is basically having to get spread out along the surface of a sphere that is like growing as you think like, is it getting bigger? In the same way that the attraction to a magnet or the attraction to an electric field or the intensity of light, all of these things that could radiate outwards, electromagnetic waves, sound waves, the intensity of sound, all of those things get weaker by the square of the distance. And it has to do with the fact that as I double the distance, the area that cone, or I guess in this case a pyramid, sweeps out will quadruple. And then here, the area that it sweeps out when I triple the distance becomes a factor of 9 larger. So because of that, and because you're essentially spreading that effect thin, like butter that is spread too thin on a piece of bread, you're basically getting a less and less effect as you go out. So that's where that factor divided by r squared comes from. Notice also that you take the mass of one object multiplied by the mass of the other object. So if I had something like the Earth and the Moon, in order to double the force by affecting the Earth, I'd have to like double the size of the Earth. But I could actually just as equally double the size of the force by doubling the mass of the Moon. Similarly, the attraction of the Earth and a pencil, like that, just a pencil that you have in your hand, the attraction between, or I have a pen in my hand, the attraction between a pen and the Earth would double if I double the mass of the pen. Or I could double the mass of the Earth. Which one of those do you think seems more reasonable? So they're treated independently. Okay, and then here's this G thing. This is very important. So when we've been calculating force, we've been just using mass times G because that's what we've been using. But it's clear that something about what we're doing is incomplete because the full formula looks like this. So what have we been skipping over? Well, if I rearrange this equation, which is what we've been using for just G, and isolate that, and then I substitute for Fg what I have up here, then I get this expression. Then the mass that's on the bottom is going to cancel with one of the masses that's in here, because this is like the mass of U, And then the mass of u again shows up in this equation, and the thing that's left over is the mass of the Earth. And so if we look, G by itself, which is called the gravitational field, sometimes called the gravitational field strength, G by itself is going to be equal to this capital G number, that's the 6.7 thing, 6.7 times 10 to the negative 11th. The mass of the Earth, which is a fixed number, it's some, 10 to the 24th kilograms or something. I forget exactly what the number is, but it's extremely big. And then divided by the R. Now, what's going to be the R value for U on the surface of the Earth? Well, if you imagine this is the Earth and this is you standing on the Earth, so the distance between your center of mass and the Earth's center of mass is functionally just the radius of the Earth. So what we do is divide by the radius of the Earth squared, and when I put all of those numbers together in a calculator, G spits out to be, you guessed it, 9.8. So it's not that I have, it's not that we didn't know how to do this calculation earlier, it's just that we didn't have this formula on hand. So I basically pre-calculated this value. I said, hey, by the way, the value you can use for G is 9.8, and since none of these numbers change on any of our regular kinematics problems, we can just use the 9.8 number for basically any problem, or round up to 10, it doesn't really matter. And we are still essentially using this formula just simplified down, because this portion of it that I've just now boxed is encapsulated by this value G, and so then you get, instead of G mm over R squared, you can just multiply M, which that number is changing. That's whether you have the mass of a pencil, a person, or a protractor. And then this G value is not really changing as long as you are not swapping to a new planet or, getting to a really high altitude. Now you might say, wait a minute, doesn't this mean that if the R value is changing, like if I jump in the air, doesn't that increase my R value, and won't that affect the force of gravity on me? Yes, it does. However, because you jumping in the air is only going to change the distance by a very small percent, it doesn't have an effect, right? It's the difference between 1,000,000 squared and 1,000,001 squared. 1,000,001 is technically bigger, but it's not really bigger as far as having an impact on the size of what you're talking about. Okay, now we're going to talk about Kepler's laws. So let's see if I can figure out how to use a computer again. Yay. Okay, so who is Kepler? What's going on? A little bit of background. Kepler was predated Newton, but came after Copernicus. And so his first big idea was, Copernicus was famous for, heliocentric model, sun in the center of the solar system, and the planets orbit around the sun as opposed to the sun orbiting around the Earth. However, Copernicus assumed that those orbits were circular, not spherical. And Kepler's first law is to say that actually those orbits are elliptical. Now, that came from just very careful measurements. And we can talk more about what an ellipse actually is, except that we don't need to. We just need to know that it is an ellipse. And therefore, that means that sometimes the planet is closer to the sun and sometimes it's farther than the sun. And that's going to be relevant for the next law. By the way, when I say law, I mean like a physics law. So that means that we're not talking about a rule that someone has to follow. We're talking about an observation that tends to never be broken. So no matter which planet I'm looking at, Earth, Mercury, Mars, Saturn, all of those planets have elliptical orbits. Okay, so Kepler's second law is a little bit outside the scope of this class. Excuse me, oh my goodness. A little bit outside the scope of this class in the sense that it has to do with sweeping out area, and it's kind of a calculus topic. We're not going to really bother ourselves too much with it, but I will explain what's going on. So as a planet comes around here, and then it hits point A, and then I start my stopwatch and I say, okay, where is this planet going to be in 3, weeks or something? So 3 weeks go by and it's here. So it's traveled from here to here. So if I take this slice of the pizza, that slice of the pizza would have, this much area. If I wait later in the year and then now I get to point E, that is, and I say, okay, let me set my timer again. I'm going to see where it goes 3 weeks from now. Now it travels way slower. So right here. It hasn't gone that far, but if you take the slice of this pizza, oops, I didn't do that very good. This area actually ends up being equal to this area. So the areas are equal. And that has to do with calculus. But the reason why it's possible is because even though they both had 3 weeks, the planet was moving faster here and moving slower here. And so that has to do with actually forces. So if you imagine the object here, let's say we're returning from being taking our journey. So I have a force from the sun that is this way, and that force has a tangential component along with a centripetal component. So it's towards the sun, but it's also a little bit in the direction I'm going. There's somewhat of an angle in here that's not a right angle. And so as a result, the sun is going to speed me up. When I get to this location, I have a force this way. And again, this is not quite a right angle. And so the sun is speeding me up. And so because of that, when I'm going this way, I'm getting faster and faster. Then I'm going to zoom around the sun, kind of overshoot, and then slow down. So look kind of like this. Can I clear this off? What happens if I do? Can I make it go away? I don't know how to make it go away. I have a laser pointer. Whoa. Okay. So basically you are here going slow. You're like, whoa, I'm kind of going slow. I'm kind of going slow. I'm getting faster, faster, faster. Whoa. Slow, 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 slow. Whoa. Slow, slow, slow. Something like that. Okay, I don't know if this is all getting captured. I hope it is. Okay, next. Kepler's third law has to do with the relationship between radius and period, and that's what you're going to be doing the lab on. So if you want to cut to this part of the video, I'll take a timestamp later and put it in the comments. This is where I start explaining how to actually do the lab. The idea is that because the Earth's orbit is also elliptical, we spend part of the year a little bit closer to the sun and part of the year farther away from the sun. So for example, we're coming up on our perihelion, which is when we are the closest to the sun, which happens in January. Now, that might seem opposite. You might be thinking, hang on, January, that's when it's cold, that's winter, that's close to the solstice. Isn't that supposed to be when we're far away from the sun? And you'd be wrong. We're actually closest to the sun. And not only are we closer to the sun, we're moving faster. We are literally moving faster through outer space because we are closer to the sun, and we've had that opportunity to accelerate as we get closer. So if you've been feeling like you have a little more energy recently, you're moving a little bit faster, you got a little pep in your step, that's because we are literally going faster around the sun, and we go slower around the sun in the summertime, when we're lazy and stuff. Hopefully you understand the seasons have not to do with how close we are to the sun, but actually the tilt of the sun. I'm not going to get into that. This is not a climate science class, but it's worth talking about. Okay, so let's take a look at the lab. It's on Canvas. It looks like this when you open it up. There's an instruction page here that explains what you're supposed to be doing, and then there's some analysis questions. I made it like a midnight blue color for thematic reasons. So our goal is basically to determine the relationship between the distance away the planet is from the sun and how long it takes for that thing to orbit. And Kepler figured this out without using Newton's laws. He didn't have gravity or calculus or anything to use. He just used astronomical data. And he plotted the relationship between R and T, and he got something that looked a little bit like this. So I have here the data that I got from NASA for all of the orbital periods. So Mercury has a period of 88 days, Earth 365, Saturn 10,000 days. And then I have their two orbiting distances, so the closer distance and the farther distance, and I've just averaged those. And then so the idea is that if I were to plot the average distance, R, can I get this out of the way? If I plot T and R, and then I plot them, I get a line, but that line is not straight. Like I've drawn a straight line, but the data clearly curves in some way. And if you look at my error term, which is this R squared term, it's like a 0.977. So it's good. They increase together. There's a positive correlation, but this is not a perfect match. And so what we're going to do is we have lots of possible perfect matches that we are going to be testing out until we find the right one. Actually, you're going to have to do all of them. And so what I want to model now is how to actually do that with this data. And so I'll take this one for an example. So maybe it's not an R versus T relationship. Maybe it's R squared versus T. So what I want to do is get all the data from the period and to put that into the T column. So I could do that by just copying and pasting, but there's another way to do it. If I click this cell here, and while I have the cell highlighted, with my finger, I touch the equal key, then an equal shows up on my screen. And now the next cell that I click, it's going to reference it, like a programming language variable. It's going to reference it. And so if I click this Mercury data cell, I can say, hey, I want in this cell, G2, I want the data from B2. That's why it says it's going to equal to B2. If I hit the enter key with my finger, then it will pop up as 88. I can do that for the next one also. I could say, okay, for this one, equal sign, click the cell I'm interested in, then hit enter, and it will copy over Venus. Or once I have it highlighted, if I see this little blue dot and I mouse over it, click it, and then drag down, you can see that outline is sort of showing up there. And if I release, it copies all of them. And that's super powerful. Now you might say, wait a minute, I could have done the same thing by just copying and pasting. Could have gone over here, hit Control C, gone over here, hit Control V, and it pops up. Yes, you're right, but that becomes more of a problem when I don't want to just copy it, I want to square it. So now, if I wanted to copy over the average orbital distance into this column, that's fine, I could do that, but how do I get this number squared without just having to put in my calculator? Well, what I can do is the same trick. So, oops, hello? Okay, so I'll put here an equal sign. I'm going to click on this data, and to square something, you multiply it by itself. So I'll hit the asterisk key, which is the multiply key, and then I will click it again. And then when I multiply that together, it gives me the square value. And by this point, the spreadsheet has figured out what's going on, and it says, oh, I bet you want to square all of those numbers. And so you can go ahead and do that by hitting the check here, and it will square all of those numbers. Another option, of course, if I didn't want to do that, I could hit the equal key, click this button, and then to execute squaring, I could also use the caret key, which is like Shift 6 on my computer. You may have different keystrokes. And then the number 2, that'll also square it, and it'll also autofill for the rest of the values. Okay, how do I actually get the graph? I want a graph that looks like this. So if I highlight the cells, so again, I'm going to click on the T or whatever and drag to highlight these cells. While they are highlighted, I'm going to take my mouse and go over to Insert, Chart. Oops, lost it. Here it is. Insert Chart. Click that. It inserted a chart. Now, if yours didn't default to a scatter chart, you might have to click here and make sure you find the scatter chart, which is towards the bottom here. But mine did default that way. It's put the R squared value on the y-axis and the t value on the x-axis. And that's why it was important to highlight the column headers, because then it uses those column headers as the labels for the graph and also the title for the graph. What I want to do is go to Customize, which is over here. Go to Series. Scroll down. Go to Trend Line. That will turn on that trend line. And then go to Show R Squared. So you can see that this is not approximated perfectly by a straight line. It's a little bit better than we had before. It's a 0.98 instead of a 0.97, but it is not still 100%. One of these is going to be a perfect match, and so you're going to go through and do the rest of those on your own. Once you've done that, you will answer these questions, and that is basically the lab. And you can check to make sure you got the right one by going back and looking at the slides if you wish. Okay, I think that is basically it. So if you have anything else any questions you have about the lab, please send me an email. Otherwise, enjoy your Thanksgiving. Keep on keeping on. And I'm just really thankful that you're taking this class and you are just putting the time and energy and effort into learning physics. I just think that's so cool. And I'm glad to be a part of that journey with you. So in that sense, I'm very thankful for you as well. So anyway, enjoy the holiday, and I will catch you later.